Hello, I'm Farhnaz Akrami, PhD student from the University of Texas at Arlington. Our paper is an empirical study of the evaluation of popular embedding models for knowledge graph completion, specifically for the task of link prediction. Embedding models learn vector representations of entities from known data in the form of subject relation object triples. These models embed each entity into a multidimensional vector. In Trans-E, which is perhaps the most well-known embedding model, a relation is also a vector, which represents a geometric transformation between the subject and object entities in the embedding space. The vectors are learned in a way such that for a training triple, the summation of the vectors of the subject entity and the relation are as close to the object entity's vector as possible. In evaluating Trans-E, given a test triple, the task is to pretend either the subject or the object entity is missing, and then use the learned vectors to rank all candidate entities based on how much these vectors deviate from the premise that subject vector plus relation vector equals object vector. Embedding models for knowledge graph completion has been a popular subject of study. This table shows how some of the most well-known models made progress on prediction accuracy over the years. For evaluation of accuracy, these studies use various metrics such as min rank and hit set K. Several benchmark datasets are commonly used for evaluation. This talk will focus on FE50K and FE50K237, which are subgraphs of freebase. The paper has details about similar observation and results using other datasets. When we started to investigate these models a couple of years ago, we soon noticed some problems with the benchmark datasets. We thus decided to thoroughly reevaluate these models. Our findings are, first, various problems of the benchmark datasets led to unrealistic inflation of the model's accuracy. Second, given the problematic data, very simple rules can challenge the accuracy of those complex machine learning models. Third, the true accuracy of the models is poor unrealistic data. Finally, the link prediction task on the problematic dataset is non-existent in the real world. The first problem is that FE50K has excessively many reverse triples. In the graph on this slide, there are two reverse triples about the same relationship between Steven Spielberg and Jurassic Park, which are depicted by the two reverse edges. 70% of triples in FE50K's training set form reverse pairs. Therefore, the embedding model could largely be just learning whether two relations form a reverse pair. For example, directed by and director. Similarly, for 70% of test triples, their reverse triples exist in the training set. For instance, the training data say Schindler's List is directed by Steven Spielberg. After the embedding model essentially learned directed by and director are reversed, it becomes trivial to predict who is the director of Schindler's List. We use a simple rule to find reverse relations. If the subject-object pairs of two relations have 80% overlap, we consider them reverse. We then use the derived reverse relations to do link prediction. The accuracy of this extremely simple model is on par with the state-of-the-art complex machine learning models. The link prediction scenario given such excessive reverse triples is non-existent in the real world. In freebase, which was used to produce FE50K, when a new fact is inserted, it would be added as a pair of reverse triples. The relations of two reverse triples are denoted explicitly by a special relation in freebase called reverse property. Therefore, there is never a scenario in which one needs to predict a triple while its reverse is already in freebase. Training a link prediction model using FP50K is thus a form of overfitting, in that the learned model is optimized for the reverse triples, which cannot be generalized to realistic settings. More precisely, this is a case of excessive data leakage. The model is trained using features that otherwise would not be available when the model is applied for real prediction. These benchmark datasets have another type of data redundancy that unrealistically inflates the model's accuracy. They have duplicate relations in which the subject-object pairs substantially overlap. Duplicate relations in FP50K come from freebase, particularly due to the concatenation of edges on a special type of nodes called CVT nodes, which represent multi-array relationships. In this example, relation number 1 in red color records football players' position considering their overall career. Relation number 2 in green color is a concatenation of two edges connected through a CVT node, representing a multi-array relationship about the position a player plays for a team. Since most players play at the same position throughout their careers, these two relations are highly redundant and we call them duplicate relations. In FP50K, all CVT nodes and their edges are removed, but the concatenated edges are kept. Out of 1,345 relations in FP50K, 168 relations form duplicate pairs. Similar to the case of reverse relations, on these duplicate relations, very simple rules can be as accurate as embedding models. We also discovered another problem due to concatenated edges around CVT nodes, which led to overestimated accuracy of embedding models. This problem shows up in what we call the Cartesian product relations. The subject-object pairs from all instance triples of such a relation form a Cartesian product. In this example, Tokyo and January are connected through a CVT node with two edges labeled climate and month. The same CVT node also connects to nodes that represent the average minimum and maximum temperature and rainfall of Tokyo in January. The concatenated edges labeled climate.month thus form the Cartesian product relation, which records the obvious fact that every city has a climate in every month. The link prediction scenario of predicting whether a city has a climate in a month is meaningless in real world. Our paper shows that a very simple method can be more accurate than trans-E on Cartesian product relations. We can view a relation as a bipartite graph between its subjects and objects. The simple method declares a relation to be a Cartesian product if the graph is close to a complete bipartite graph based on a threshold. For link prediction, the simple method just considers every edge in the complete bipartite graph to be true. Earlier in the talk, I provided a list of our findings, as shown here again. I discussed point number 2 and 4 in previous slides. Regarding point number 1 and 3, we did experiments to find out true accuracy of the embedding models using a dataset with less of the aforementioned problems. One such dataset is FP50K237, which is a subset of FP50K where most reverse and duplicate relations are removed. By comparing the model's accuracy on both FP50K and FP50K237, we found point number 1. The performance of all methods worsens considerably after removal of reverse and duplicate relations. We also observe point number 3, the absolute accuracy of all models is poor on the more realistic dataset FP50K237. This shows that existing models are ineffective for real-world link prediction tasks. Another observation is that many successors of Trans-E that outperform Trans-E on FV50K attain similar or even worse performance on FV50K237. We hypothesized that these models improve mostly on reverse and duplicate triples, and hence, after removing those triples, they don't exhibit clear advantage. Our findings verified this hypothesis. We looked at the test triples on which these models outperform Trans-E. It turns out a large percentage of such triples have reverse or duplicate triples in the training set. For instance, the percentage is 78% for conv-E. The 2015 paper from Totanova and Chen noted the reverse relation problem in FV50K and created FV50K237. Similarly, the 2018 paper from Detmers and others introduced WN18RR in order to remove the reverse relations in WN18. There have been a few other studies on the evaluation of embedding models, including our own preliminary work in 2018. Our paper provides the first systematic study with the main objective of assessing the true effectiveness of embedding models when unrealistic data are removed. It also provides a thorough investigation of the data redundancy problem and identifies Cartesian product relations. The take-home messages are that our community hasn't been solving real-world challenges in link prediction, and the current link prediction methods have poor accuracy on realistic data. And finally, we shouldn't use FV50K, WN18, and YAGU310 at all. You can find all the codes, datasets, and results of our study in our public GitHub repository. Thank you for listening.